We're live again. Live again. So much to do. Oh, what the heck? All right. All right. Kinetics and equilibrium. Everyone's favorite. We all know what this is going to include. Shifting. All right. Oops, sent that to the wrong class. My bad. Did not mean to send that to third block. All right, let me just send out a quick announcement again. All right, so we're doing kinetics and equilibrium, everyone's favorite unit. Not really. No one likes this unit, but that's okay because we're going to get through it together. All right, so nope, because that's not on the Regents. All right, kinetics. We'll start there because I think kinetics is easier. There's one hard aspect of kinetics, which is those graphs with like activation energy and stuff, and that's just no fun. So when you think kinetics, we think rate. How fast is this reaction? And a lot of stuff in chemistry is how can we make the reaction go faster? How can we make the rate go up and the time go down? I want this reaction to go faster. If I want to travel from here to Saratoga, because I live in Clifton Park, I'm going to drive on the highway, because I can drive faster on the highway, so I can get to Saratoga faster, versus if I took like Route 9, and I hit a bunch of traffic lights, and then general traffic, it would take me a day. So, how can we make a chemical reaction proceed at a faster rate, aka a shorter amount of time? Let me make that time, that looks like a D. Doop. So, it's all about collisions. If we can make collisions go up, we will make the rate go up. We need these particles to collide. If these particles are not colliding, they are not reacting, and therefore, they are not proceeding at a faster rate. And if they're not reacting, you're not making any products. And that's the goal. We need to take a few things and get them to collide, or take one thing and get it to collide with itself so we can get a reaction to proceed. And there's a few ways we can make a reaction proceed faster. 1. Increase the temperature. If you increase the temperature, increasing the kinetic energy, which means these things are going to start moving faster and faster and faster, which gives us a higher probability that they'll collide, and they will collide with enough energy and at the right spot, and we get a reaction to occur. Another way, you can increase the surface area. And one of the classic ways we can represent this is like in my class, we did a lab with Alka-Seltzer. And we took Alka-Seltzer and we put it in a film canister and we watched them explode and make like a little rocket. If you crush the Alka-Seltzer, you increase the surface area. You're taking one large tablet, right? And that one large tablet has the surface on top and a little bit on the sides and the surface on the bottom. Well, if you crush it, you're exposing all of those surfaces to multiple different sites. You're just making it easier to react. So if you increase the surface area, you'll get more collisions, you will get a faster reaction. Increase the concentration, aka increase the molarity, the moles per liter. basically, if you have more stuff, there's more collisions that will occur, which means they will make more products. And I'd like you to visualize this one in like a box. And we'll say this one is 0.1 molar concentrated, and this one is 1 molar concentrated. So one of them has much more stuff than the other. So this one we can pretend has like this many particles, versus this one has this many particles. The chances that these collide and make your products is much higher than these will collide and make products. So if you increase the concentration, you're going to get a faster reaction. You can increase the pressure on a gas basically just take the size of your container and shrink it down. But that only works for gases because solids and liquids, if we draw like a particle diagram for a solid, just to review that, solids are already pretty close together. They're in that crystal structure. They have that rigid shape. And if I take the container and make it this big, that's really not going to affect my solid at all. And liquids are more or less the same way. When you draw a liquid, you're basically just spreading it across the bottom of your container. Even if I shrink my container, that's not smaller. Even if you shrink the container, yeah, you're pushing them closer together, but it's not really affecting how they're going to react. All they're going to do is just adapt to the size of your container. Versus if you take a gas, gases in a container are really far spread. They are spread out. That kind of looks like a dice. And if you shrink the container, now they're all going to be nudged up together, and gases are going to be moving. Gases are going fast. So now they're going to collide more and therefore have a faster reaction. So if you injure, aka decrease the volume, push down on that container, the gases will react more and therefore proceed at a faster rate. And then 5, add a catalyst. I'm getting a few texts. I'm going to double check that they're not on Remind. I meant to say maze and not puzzle in my text. Sorry, third block. I can't type tonight. I just said world. Anyway. If you add a catalyst, and we'll go over more of what that means later, you will increase the collisions and get the reaction to proceed at a faster rate. Either way, what are all of these things doing? Why does this allow them to collide more? Well, a reaction needs proper energy and proper orientation. So when these things collide, they need to collide with enough force. So if you're at a really low temperature and these particles are moving super slow, they're going to hit each other and then just kind of bounce off and not doing anything. It's like when you throw a water balloon and you just throw it too slow and you're like really trying to hit this person, trying to embarrass them a little bit, and it hits them and it just kind of bounces off and you just feel so deflated, like, oh, that did nothing. That's what we mean by proper energy. You gotta really chuck these things at each other so they can hit and react. But they also have to hit in the right spot. So if I like really slowly try to put my key in the ignition to start my car, I'm not going to be able to push it in if I'm too weak. And I know you don't have to be that strong, but if I put it in with the right energy and start my car, that's great. But if my key is faced the wrong way, no matter what I do, I'm not jamming that key into my ignition and starting my car. If I want to put my hands together like this, I can't do that like this. So it's all about proper orientation. Like if you're doing like the very stereotypical I'm praying, you can't do the stereotypical I'm praying like this. This doesn't look like, this looks like you're reading a book. This is not the orientation to show that I'm praying. This is. Or if you want to do the book one, you don't read a book like this. Some of you are like, I don't read books, Mr. G. Your choice. But what I mean by proper orientation is they have to collide at the right spot in order for it to occur. And that is all about kinetics and collisions. Let's see. What's next? Let's do these graphs. What graphs? These graphs. Alright, so you're always going to see these graphs. Probably one of them on your Regents. Okay? So we got potential energy on the y-axis. I'll put some numbers here. 50, 80, 110. And that scale makes no sense. Just don't worry about it. What do each of these things represent? What is this? Okay, so right where you start, keep in mind you will never start at 0, ever. Because when you're doing a reaction, let's say this was, let me pick an endothermic reaction. Let me take the time to go over table I right now. So table I is the heats of your reactions, aka delta, aka is this endo or exothermic, at these conditions. So if you see these conditions pop up in a question, and then something about endo or exothermic pop up in the question, like, which one of these reactions is exothermic? And there's no other hints given, like energy is not given anywhere in the problem, delta H is not given anywhere in the problem. That's usually an indicator you got to go to table I. And what table I is showing is 25 random reactions, and if they're exothermic, aka negative delta H, or endothermic, aka positive delta H. Now keep in mind, even if it's negative, when you put it in your reaction, you will still put it on the right side with a plus sign. And I know that's confusing, and I know at least a few students in my class like to put subtraction signs in chemical reactions. Never do that. What this is saying is these two ingredients will collide and react and make carbon dioxide and make or produce heat. So we always use that plus sign, and to show that it's leaving the reaction, to show that it has a negative delta H, to show that it's exothermic, we will just write it on the right-hand side of the arrow to show that it is leaving, to show that it's being produced. And if you can't remember if a negative symbol is exo or endothermic, on the bottom of table H, it tells you a minus sign indicates an exothermic reaction. So you don't have to memorize that. So I am going to do this N2O2 make 2NO reaction here. So let's say this was a graph for this reaction. These reactants exist with some amount of energy. They're moving. They have energy within them. And if they didn't, they wouldn't exist. So where you start is the energy of reactants. So in this case, the energy within N2 and O2. That's where you start. Now, in order for this reaction to occur, you need to input energy. Okay? At their given state, they'll collide with each other, but they're not going to create anything. So you have to ramp up the energy. You have to input some heat or input something to get them moving so they collide with the right amount of energy. When you look at the region right here, from where you start to the peak of the hill, this is called the activation energy. Which for this reaction would just be 110 minus 50. And that would give you 60. And whatever the units are, joules, kilojoules, these have units. We're just going through this quicker. So, what is the activation energy? Well, that means we have to input 60 energy units in order for this reaction to start. To get this reaction to start, we have to take it from 50 all the way up to 110, aka input 60 units of energy, 60 joules, 60 kilojoules. And then when they react, they will form products. In this case, 2NO. So here is the energy of your products. So when we look at this curve, we start at 50 and we end at 80. There has been a net gain of heat. So we started at 50, we end at 80, and the products minus the reactants, 80 minus 50 is a positive 30. Which means our delta H is plus 30. The heat of the reaction, that's a lot of ways you're going to see this. The heat of the reaction is plus 30. The products minus reactants, the heat of the reaction is plus 30. And since it's plus, it's endothermic. There has been a net gain of heat. Now, if the graph was the other way around, here's your reactants, here's your products. Let's say this was 80 and this was 50. You do products minus reactants, you'll get negative 30. Negative 30 is your delta H, which means you're thermic. What if they phrase the question as, what's the activation energy for the reaction in reverse? So if you have to do it in reverse, 50, 110, 80, all that means is you're going to read it this way. From right to left instead of left to right. So everything in reverse, so that your reactants energy would be 80, your products energy would be 50, your activation energy would be this region right here, 110 minus 80, and your heat of reaction, your delta H would be, since 50 is your products now, 50 minus 80, which would be negative 30, which would be exothermic. So if you have to read this in reverse, read it in reverse, and do everything the same way that you just did. Go from where you start to the top of the peak. That's your activation energy. That's the energy to get the reaction to begin. Look at where you end. That's the products. Look at where you begin. That's the reactants. And get the heat of the reaction. Subtract products minus reaction. Products minus reactants. And if it's negative, it's exo. And if it's positive, it's endo. Now, what does a catalyst do? What is the role of a catalyst? A catalyst will lower the activation energy by providing an alternate reaction pathway. And that's the language they like. It will provide an alternate path. It doesn't change where you start. It doesn't change where you end. All it does is get you there in a different path. It's like trying to leave the building. If you're in your 4th block class and you hear that bell ring, you could take the long way out. You could go circumvent the whole school, go say hi to a few teachers, stop by the cafeteria, get something out of the vending machine. Or you could take the quicker pathway. You can take an alternate pathway, a shortcut. The path that gets you out from your class and into your car or bus or wherever you're going as fast as possible. And they represent that on a potential energy diagram. So these diagrams I've been drawing are called potential energy diagrams. The same way. Let's say you take that original reaction we had. A catalyst will start at the same spot and then just make that activation energy lower. So we start at the same spot and we end at the same spot. All we're doing is getting there on a different path. You can go down the original path, or you could take the path of the activation energy. Fine, you start and end at the same place. So there's going to be a bunch of practice problems with these, because you just need practice with them. They're weird looking. A lot of chemistry is weird. You know this. We all know this. It takes a lot of work. But we'll get there. We'll get there. The only other thing I wanted to mention, let me copy down that reaction from before. Was it N2 and O2 make 2NO? Now, according to table I, if that reaction proceeds at exactly those ratios, it will endothermically absorb 182.6 kilojoules of heat. So your delta H is 182.6 kilojoules. I think those units were kilojoules. Meaning if we were to add that to the reaction, that 182.6 would be entering the reaction. Part of the reactants. That heat is going in. Now, sometimes they will change these ratios here. So right now this is a 1 to 1 to 2 ratio. Some questions would ask, what if 4 moles of NO was produced? So what if this reaction proceeded as normal and it produced 4 moles of NO instead of 2? Well, you just have to scale everything up proportionally. Going from 2NO to 4NO is a multiple of 2. I multiplied it by 2. So I have to take everything over here to make that 4NO and multiply it by 2. So now I have 182.6 times 2, which would be 2, 5, 6, 2. That looks right. Kilojoules of heat being absorbed and reacting with 2N2 and 2O2. So whenever they change the moles of the problem, do that to every. So you can do the same thing. What if it said 0.5 moles of N2 reacted? Well, if I took one N2 and divided it by 2, to 0.5, take everything over here and divide it by 2, and take everything over here and divide it by 2. What you do to one thing, do to everything. They're not going to trick you with like limiting reactants and all that stuff if your teacher mentioned those on the Regents. So just keep that in mind. All right. Equilibrium. Oh boy. Equilibrium. We're going to do everything before we do shifting, because shifting is such a pain. Equilibrium means equal rates. So at equilibrium, you will often see it represented as, I'm going to be using this reaction all the time. So 2NH3, 3. These double arrows. And what these double arrows mean, the speed at which N2 and H2 react to make NH3 is the same as NH3 breaking down and making N2 and H2. So N2 and H2 react, make NH3, is the same rate at which NH3 breaks down and makes these two. So these are just going back and forth at equal rates. Equal rates. The other thing about equilibrium is this is alliterative. Constant concentrations. So at equilibrium, the rate at which these reactions are occurring is equal, and the amounts are staying constant. So the amounts don't have to be equal. The amounts just will remain the same. And we did a water lab, kind of silly, but it showed this. As long as you and your partner took the water in the straws, dropped them into your graduated cylinders at equal rates, you saw a graph that looked like this. Or something similar to this. At some point, the concentrations of your water in both graduated cylinders remain the same. Or sorry, didn't remain the same, stayed constant. They didn't equal each other. The water in graduated cylinder A wasn't the same amount as the water in graduated cylinder B, but the amounts did not change. They got constant. So the concentrations will remain constant at equilibrium, and the rates will be equal at equilibrium. So just keep that in mind. Equilibrium is what we describe as dynamic. And all that means is that it's changing. So all reactions at equilibrium will adapt to the conditions you put them at, which makes it dynamic. So they have to go through changes to reach equilibrium again. You can see equilibrium as a phase equilibrium. So that just means if you have like chlorine gas is at equilibrium with chlorine as a liquid, the phases are staying the same. Or sorry, the phases are what's changing. But the substances themselves are staying the same. So that would be phase equilibrium. So if you found like the perfect temperature where water is both melting and freezing, you have phase equilibrium. Look for a change in phase, but look for no change in the substance that's changing phase. Okay? So that's phase equilibrium. You can have solution equilibrium. And the first one I showed you with making ammonia, this is chemical equilibrium. Chemical equilibrium because two substances, the substances on the left and the right are the same atoms. They're both N's and H's, but on one side they're elements. They're diatomic atoms. and on the other side, it's a compound. It's ammonia. So that's chemical equilibrium. Phase equilibrium is when the substances are staying the same. They're just changing what phase they're in, solid, liquid, or gas. And then solution equilibrium is when you're at that like perfect dissolving crystallization. So you're dissolving salt in water. And it's an equilibrium between itself as a solid crystal and itself as an aqueous particle dissolved in water. So that's solution equilibrium. And then the top part was chemical equilibrium, where all that means is the rate at which you're breaking bonds is the rate at which you're forming bonds. So that barf, breaking absorbs energy, releasing energy is forming bonds. Ooh, forming bonds. That rate is the same. Break, form. Sorry. Break, form. Break, form. That rate is the same. NH3, N2 and H2. NH3, N2 and H2. NH3, N2 and H2. That rate stays the same. But you can disrupt equilibrium, and that's when we get to Le Chatelier, aka shifts. When you or something in nature disrupts a reaction that is in a happy place, that is in a spot of equilibrium, the reaction will respond and shift, increase the rate of the reaction on one side to the other to get back at equilibrium again. So remember, when we said at equilibrium, the rates were the same, and the concentrations reach this constant point where they're not equal, but they're not changing anymore. If you do something to mess this up, or if something happens in nature that messes up this equilibrium, the reaction is going to respond to this in a way to get it back to equilibrium. And there's three main changes. So, let me just look up, I think ammonia is on table I. I'm going to look up its 91.8. Okay, so when ammonia is being formed, when you take nitrogen and react it with oxygen to form ammonia, and these are all gases. Let me write it smaller, because I can't fit what I wanted to fit. When nitrogen and hydrogen react at equilibrium to make ammonia, it releases 91.8 kilojoules of heat. So this is exothermic. And this is in a happy place. But if you came in and disrupted this in some way, the reaction is going to fight you back. So if you came in and you just threw in a whole bunch more nitrogen gas into this equation, what's going to happen? Well, use the principles we just talked about before with kinetics. If there's more nitrogen gas in this container, there is more nitrogen and hydrogen that's going to be colliding than the ammonia is to break down more nitrogens and hydrogens. So keep in mind, this reaction was happy doing this. Sorry, I did it backwards again. Taking two things and forming one, and then that one thing going back and forming two. And this was in a good spot. Now you came in and you threw in a bunch more ingredients over here. So much more that now these are coming in and making more NH3 than NH3 is breaking down to make N2 and H2. So it's almost going 2 to 3 times. So make 1, 2, 3 NH3. NH3 breaks down. 1, 2, 3 NH3. NH3 breaks down. So the NH3 can't keep up with the reaction in the same rate at which NH3 is being formed. So what kind of ends up happening is you can represent this reaction going like this now, where the forward direction, going from left to right, is now going much faster than the reverse direction, going right to left, because of this increase. And when that happens, how the reaction will respond to get back to equilibrium is your amount of NH3 is going to start increasing because of that increased forward rate. And because of that, that means if you're forming more NH3, then NH3 is going backwards. If you're going forwards at a faster rate than you're going backwards, if you're going forward at a faster rate than you're going backwards, the concentration of N2 and H2 is going to start decreasing. So as soon as you throw in a bunch of N2, it's just going to react. It's there. And the amount of N2 you just threw in is going to start disappearing very quickly. So when you see this occur, we say this is a shift to the right. Because of that arrow representation I just showed. So the reaction is going to shift right. It's going to increase the rate of going towards the right side until it gets back at equilibrium again. Until this increase that you caused goes away and it becomes constant concentrations and equal rates. Same reaction. All right, pause if you want to see this again. But I just want to keep the reaction up on the page. What if you decrease N2? Or I'll just pick a different one. Decrease H2. So now you've taken H2 and you've just taken it away. It's not in the reaction anymore. This means now there's less stuff on the left side than there is on the right side. And since the H2 is gone, there's less H2 to react with N2. So NH3 now is going to be producing more of the ingredients on the left, then the left can come and make more NH3. So if you remove H2, you're going to get more NH3 breaking down than NH3 being made. Which means the reverse rate is going much faster than the forward rate because there's less stuff going from left to right reacting because you've removed it. So this will cause a decrease in NH3 because there's less H2 reacting to form NH3, which means NH3 is breaking down faster than N2 and H2 are reacting. So you're going to get an increase of N2 and H2 until we reach equilibrium again. So this is a shift left. So generally speaking, if you increase the concentration of X, it will shift away from X. If you decrease the concentration of X, it will shift towards X, whatever side X is on. Okay, so if you increase the concentration of X, it will shift away from it. Increase the side opposite of X. If you decrease the concentration of X, it will shift towards X. Increase the concentration the side X is on. So if you increase N2 or H2, it will shift for NH3, and less N2 and H2 will be seen. If you increase NH3, it will shift towards N2 and H2, make more N2 and H2, and there will be less NH3. If you decrease N2 or H2, it will shift towards N2 and H2. It will shift left, make more N2 and H2 than NH3 is being made. So N2 and H2 will go up, NH3 will go down. And if you remove NH3, there is less breaking down to make the N2 and H2. So the N2 and H2 are going to react more. The N2 and H2 are going to decrease, and the NH3 will increase. Temperature is the same thing as concentration. Identify where your heat is. We said the delta H here was negative 91.8, which means heat is being released. So if you increase the temperature or you increase the heat, you will see this shift away from temperature. You increase the concentration of X, you shift away from X. And we can include temperature here. So even though we're not increasing the concentration of heat, it's the same idea as concentration. So if you increase temperature here, we're seeing a huge increase in the heat, which means we're seeing an increase in something on the product side, which means we've disrupted equilibrium. The products are more outnumbered than the reactants, and since there are more products now, you're going to see this kind of shift. The products are breaking down faster to make N2 and H2 than N2 and H2 are reacting to make NH. So when you increase temperature, it's going to shift left. Because temperature is on the right. So if you increase it, heat is on the right-hand side. So if you increase it, it's going to shift away from it. And this is going to make more N2 and H2 and make less NH3. And decreasing temperature in this reaction would do the opposite. So if you decrease temperature, it will shift right. It's exactly like concentration. You decrease the concentration of something, shift in the direction of that something. It will shift right and increase NH3 and decrease N2/H2. All right, pressure is the weird one. So let's do that, and that's it for these shifting. Increase in pressure, put down here by the general rules. Shift to less gas. Decrease in pressure, shift to more gas. So an increase in pressure is the same as a decrease in volume. If you've increased the pressure, you've decreased the volume, which means the reaction wants to shift towards a side where there's less stuff, because the reaction wants to do the opposite of you. And the way it could do that is shift to the side where there's less gas, because where there's less gas, there's more volume, and where there's more volume, there's less pressure. So if you enter, the reaction is going to respond to your change by trying to do the opposite of your change by shifting to the side where there's less gas. And in this reaction, if I increase the pressure, I look here, I see 1 N2 and 3 H2 for a total of 4 moles of gas on the left side. And over here, I see 2 NH3 and some heat. So there's 2 moles of gas on the left side. So an increase in pressure will shift to a side where there's less pressure, which is a side where there's more volume, which is the side where there's less gas. So this shifts right. So we'll see an increase in the production of NH3 and a decrease in the production of N2 and H2. Pressure is the hardest one. A decrease in pressure for the reaction above will do the opposite and shift left. Increase in pressure is an increase, and a decrease in pressure being an increase in volume means the reaction wants to do the opposite and try to increase the pressure again, try to decrease the amount of volume that you've just created. And the only way the reaction knows how to do this is to shift to a side where there's more pressure. Shift to a side where there's more stuff, the side with less volume, which in this reaction is the left side, because that's where there's more gas. So this is going to cause an increase in the production of N2 and H2 and a decrease in the amount of NH3. Whew, shifting's a pain. You need to know about chemical reactions to kind of end on a good note. Is reactions want to be spontaneous. A reaction would love to be spontaneous. I don't want to say equals. I can't draw a heart. But reactions love, ooh, terrible heart, spontaneous. And to be a spontaneous reaction, we need low energy and we need high entropy.